Hey Priya, can you hear me? Okay, how about now? Can you hear me now? I think I think I did it. I think I worked it out. Can you hear me now? Yay! Excellent. All right, let's go. So basically, at the moment, I'm going to be doing this YouTube stuff evenings, and the reason for that is that most people are at college in the day and they all have different schedules. So finding a time when everyone can do is just not going to work. So I'm going to do evenings, like 7:30. Pretty much I'm free 7:30 onwards, so I'm pretty much all yours, subject to my health, which, as you can hear, is currently not perfect. In fact, it's bad at the moment, but subject to that. And what I want to do is just come on here and do maths with you, basically, and not try to make a big channel and not try to make, like, have loads of people in here and not need to feel like I need to be like really well and really energetic and really full of like health to be able to do these sessions with you. Otherwise I just won't do it, because that doesn't happen enough. So I just want it to be us, and we do maths together, and this is a good forum for us to do it on. So two things today to get started. One of them is I'm going to talk to you about the year 2 pure and how I'm going to support you with the year 2 pure over the next 27 weeks till the exams. But first I'm going to start with the mechanics, because this is something we can actually fix, okay? This is something that lots of people have been worried about, but we can fix this. This can be okay. The second year mechanics is a tiny extension of the first year mechanics. If we can get the first year mechanics confident, then literally it'll take me an hour to teach you the whole of the second year mechanics. It's tiny. So there are 3 topics in the first year mechanics. In the second year there's 4, because you do an extra topic called moments, which is about whether or not things, like, imagine you've got a seesaw, whether or not the seesaw tilts. It's called moments. But other than that, you have 3 topics. F equals ma, constant acceleration, variable acceleration. Now VT graphs is a topic in the sense that they ask you questions about it, but really VT graphs is just something we can use for constant acceleration problems, or we can use the VT graph for variable acceleration problems, and we will use it for both. So I want to keep it as a kind of sub-topic in your mind, so that we just have these 3. Second year 4 add-on moments, first year 3. The way to tell that you have an F equals ma problem is literally that they mention the mass. That's it. Well, no, there's one other thing. But any question where they tell you the mass, they ask for the mass, they say the mass is m kilograms, anything to do with the mass, you need to write down F equals ma. Okay. The only other time that you're going to be using F equals ma is when they give you forces. So that might be that they describe the situation, or they might give you a force diagram and they talk about equilibrium. So if something's in equilibrium, there is no acceleration. It's not accelerating. It might be moving with a constant speed, but it's not accelerating. The velocity is not changing in any way. So if you have something that's in equilibrium, then the acceleration is 0, which means Newton's second law says F equals 0, which is saying all of the forces, if we add them all up, will equal 0. Now, usually the way that we use that isn't that we put all of the forces equal 0. Usually what we'll do is say all of the forces that way must equal all of the forces that way. And that's usually how we use it. But we're still actually using F equals ma. We're just using it with a as 0. And then we're moving all of the negative bits to the other side to create an equation. So you're looking for the word mass, any mention of mass, or they give you forces and the particles in equilibrium. Now, F equals ma, that Newton's second law, it can be used where F is just a number, because we're just doing one-dimensional motion. So this could just be a number, magnitude of the force, and acceleration is just a number. Or we could have F as a vector and A as a vector, 2 dimensions. Or you could even have F has got T's in it. So the force keeps changing at different times. It's not a consistent force the whole time, not a constant force. Depends what time it is. And then that means that A is also not constant. A has also got T's in it. A is also changing as T changes. So when you've got F equals ma, you can have number equals number number, vector equals number vector, or you can have, what was my third one? You can have, or variable force is the mass times a variable acceleration. This is king for mechanics, F equals ma. Next one I'm going to talk about is variable acceleration, because it's the easiest to spot, and what we want is to be able to look at a question and know what we need to write down, which formula we need to write down. Variable acceleration will either have x or v or a, and there are t's in the equation. So the question is blah 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 particle blah blah stuff, and then an equation with t's in it. That means we know that we've got a variable acceleration. In exams, that means we know we've got variable acceleration. Constant acceleration, you can do it by sort of ruling out the other two. It doesn't mention mass, it's not giving me forces and telling me something's in equilibrium, it's not giving me an equation with t's in, so it must be SUVAT, which is our constant acceleration equations. But you are specifically looking for either the words constant acceleration, or they give you a vector that's the acceleration and it's got no t's in it. So maybe they give you like something like that. That's constant. No t's means not changing, constant. These problems we are going to be using SUVAT. And yeah, we need to go into SUVAT and like the dangers and how they make it complicated and all that sort of thing, but we'll be using SUVAT. Variable acceleration, we're going to be using calculus, differentiation and integration. Now, VT graphs have time on the horizontal axis and they have velocity on the vertical axis. There's no rule that says that you're only allowed to draw a VT graph if the acceleration is constant. You can draw a VT graph if the acceleration is variable. It'll just be curved instead of being made up of straight lines. So a VT graph associated with constant acceleration will look like this. Notice that I put the t-axis deliberately right in the middle. I didn't put it at the bottom because lots of motion is forwards and then backwards. It doesn't have to be forwards, forwards, forwards. And all the stuff at the top above the t-axis, that's all stuff that's happening forwards, and all the stuff at the bottom below the axis, that's stuff that's happening backwards. And your particle can easily go forwards, backwards, forwards again, all sorts of stuff like that. So I think having the backwards, which is the bit below the t-axis, having access to that space in case your particle goes backwards for a while, that's really handy to think about. Now, if you've got a particle which is moving with constant acceleration, then this will be built up of straight lines. It'll look something like this, blah blah. Whereas if we have got variable acceleration, we can still draw a VT graph and it's still forward motion at the top and backwards motion at the bottom, but now it's going to be curved. This sort of thing. That's the only difference. Now, in terms of when do you need to use a VT graph, pretty much universally, like this is 99.95% of the questions you're going to get. If they say draw this is silly, I know, but if they say draw a VT graph, then you're going to be using a VT graph. And if they give you a VT graph, then obviously you're using a VT graph. But there is another time when we would use a VT graph, and that is when we're solving a variable acceleration problem. Now we'll go more into this when we deal with variable acceleration, but one of the things that you learn about VT graphs is only two things. One, the gradient is the acceleration of the particle at that time. Two, The area between the t-axis and the graph is the distance travelled in that little time period. Now, you know from first year integration that if we integrate this guy all the way from the origin across to there, we are not going to get this area at this area. We're going to get that area minus that area. And that's the classic trick that they do. They put in something, they give you the velocity, they ask you for the distance, everyone integrates, puts in 0 and 10, gets it wrong because actually the particle went forwards then backwards. So what they've actually found is the displacement, not the distance travelled. So I'm going to put a note here that we are going to be using the VT graph. If we do any integration, definitely, if we're going to integrate velocity to get distance or displacement, for sure, we want to have a look at that VT graph, check if it goes negative, which means the particle changes direction for a while. But even if we're not, having that VT graph as a reference is going to be really, really helpful. Okay, 3 topics. F equals ma, you know what to look for. Constant acceleration, you know what to look for. Variable acceleration, you know what to look for. VT graphs, you know what to look for. We're going to go through, I'm hoping this week, each of those in turn, and I'll show you the questions, and I'll show you that every question is exactly the same. All exactly the same. We do the same steps every time. And those steps essentially are that we already know what formula we're going to use, because we know if we need F equals ma, and we know if we need suvat, and we know if we need to use x and v and a and differentiate and integrate. Then we're going to take the information from the question, put it into the formulae that we need, suvat or F equals ma, or x or v or a with t's in, and then use simultaneous equations. This is going to just unlock every single question that we do. Okay, that is enough on mechanics for now. We'll come back to this tomorrow and start working our way through these 3 guys and making sure that all 3 types are totally fine and that we know all of the examiner tricks and we know all of the main techniques and that we've practiced the simultaneous equations that come out. Okay, next. Oh, and by the way, in a minute, so we're going to do a little bit of pure and then it'll be over to you and we can keep going until you get tired or I get tired, which will probably, actually I don't know which one that will be. We'll see. But if you've got a topic or a question that you want me to do, then please do let me know so that we can go over it. So, year 2 pure. What we've got here is on the left hand side, the 3 most important things. These really form the basis of so many questions that you're going to do. A load in mechanics, none in stats. You don't use differentiation or integration or trigonometry in stats, but you do in mechanics. Plus, in the pure, there are loads and loads of different questions that include differentiation and integration and trig. Loads. So these are huge. These are going to be, in the end, about 8 marks for these each. 8 for differentiation, 8 for integration, and 8 for trig. More. That's per question, and then you get a couple of questions on differentiation, a couple on integration, and a couple on trig. So you're talking big marks. Sometimes you can get 50% of the pure marks just for those 3 topics. As we go to the right, it's getting simpler in terms of the question style, and it's getting fewer marks. Okay, so as we go across to the right, if I go all the way to the right, we've got things like partial fractions. I just want to use that pen, it's better. We've got partial fractions and we've got things like binomial expansion. And these are going to be worth about 5 marks. Okay, we can do that, Priya, for sure. Moments, basically, which is that 4th topic. But that, yeah, you'll see actually, that'll be a good demonstration of how important the first year F equals ma is, because F equals ma, like, times a million is what we need in moments. That same strategy of equations and simultaneous equations and forces. Okay, so all the way over there we've got things that are worth about 5 marks, then we've got things worth about 6 marks, things worth about 7 marks. Now I want to focus in these sessions on building you a really strong spine of marks, a really strong, like, thread that runs through you where the differentiation and the integration and the trig are as confident as we can possibly make them, which means that we chip away at them, because these are difficult topics on the left hand side. The other ones, we can cover those. I can tell you about it, I can teach you, I can go through these pretty quickly. Once I've taught you, you can more or less understand any of the questions that are set, and then it's just a case of practice. Whereas the differentiation and the integration and the trig, even really, really top students need the repetition. Come back to it, come back to it, come back to it, over and over and over. So that's what we're going to do. We're going to do every single time I see you a bit of differentiation, a bit of integration and trig, building up slowly over the year, and then we'll add on bits and bobs as we go along, but the central spine will be there because we're starting it right now. Now this document you've all got, let me know if you haven't got it. This is the Chile ratings. So this is a reference guide for you about how long a topic should take you to get confident with. The ones on the right, no one is confident with them straight away. They take a lot of practice, they take a lot of coming back to. On the left hand side, these things should be fine. If you're not finding the things on the left hand side okay as you learn them, then just give me a shout, because we can fix those really super quickly and then you'll be totally fine with them. And then obviously 2 chilies in the middle is somewhere in the middle. It's not going to just click, but once you've done 8, 10 questions, it will click and then you'll be okay. Okay, most important rule. So I'm going to give you a minute. I'm not going to speak. I want you to jot down the 10 derivatives, just on a bit of paper. Oh, okay, Donia, I will. Okay, I don't have your email because we're not doing one-to-ones. If you do want to do a one-to-one, the link is in the channel description. But I think I can link documents in the description. Can I? I will try. I'll try to link the document up in the description. Because I think it's useful when you're learning to have some reference point for how you're finding a particular topic, and whether or not it's totally natural for that to take a long time to get confident with. Okay, 10 derivatives. You only need to memorize these, nothing else, just these. The ones that start with a C, they are negative. The other ones are not negative. The derivative of sine is cos, the derivative of cos is minus sine. So they're like a little pair. Tan and sec are like a little pair as well. Sec being 1 over cos, sec x is 1 over cos x. So tan and sec, in terms of their derivatives and also Pythagorean identities, they form a little friendship. So the derivative of tan is sec x multiplied by sec x, whereas the derivative of sec x is sec x multiplied by tan x. Now, we would never write sec x because we've got squared notation, so I'm not going to write it like that, but you can see that relationship. And actually I'll leave it there for a sec because it's the same relationship between cosec and cot. So the derivative of cot is minus cosec cosec, whereas the derivative of cosec is minus cosec cot. So really similar relationship between those derivatives. I'm never sure with these whether learning patterns is a good idea or whether just memorize them. That's not squared there, no. Squared is here and squared is here. So, and it's totally up to you and your brain whether you like seeing those little patterns or whether you just think, no, I'm just going to write them out loads of times until I remember. E to the x, the derivative is, well, strictly speaking, the derivative is e to the x ln e. And that means that really there are 9 derivatives, not 10, because the derivative of 2 to the x is 2 to the x ln 2, and the derivative of 10 to the x is 10 to the x ln 10, and the derivative of 7 to the x is 7 to the x ln 7, etc. But ln e is 1, so we don't write it, which makes us feel like the derivative of e is different. Now the derivative of e to the x is special, I grant you. The derivative of e to the x is e to the x. That's not nothing. That's kind of the definition of what e, the number, is. But in terms of memorizing derivatives and knowing how many functions you have to know the derivatives of, you could say that there's 10 or you could say that there's 9, depending on whether you want to think of these as the same or different. Ln x, the derivative is 1 over x, x to the n, the derivative is that. Okay, we need to get those in your brain as soon as possible. But more important than that, we need to practice using the chain rule. This is way more important than the product rule or the quotient rule. It is absolutely fundamental to the whole of integration. It's really, really important. So first thing to note with these guys is that I deliberately put a little number at the front because I found that this number that kind of lives at the front of functions a lot of the time, it can throw, oh, I didn't put it on there, sorry. It can throw students, and it doesn't need to throw you. It just sits there. Just ignore it. Well, don't ignore it like it disappears, but just don't worry about it. It just sits at the front, and whatever your derivative is, it's going to be that number multiplied by the derivative. So same here, same here. Any number at the front, don't worry about it. It's just a multiplier at the front, and it's just going to sit at the front. Okay, there are only 10/9 things that we differentiate. Therefore, each thing that you're asked to differentiate is one of those 9/10, definitely, because there are no others. So we have to look at the function and we have to say, which of the 10 are you? Now, all of these are the 10. Sine is there, cos is there, cot is here. This is e to the, this is 2 to the, and this is ln. But I changed all of the x's, and this is where the chain rule comes in. So have I got a highlighter? Let's try this one. So all of these, I didn't just put an x there. I put a 2x or a 4x or a half x or a minus 3x squared or a 4x or a 2x. Doesn't matter. I put something else in this position. So technically you do not know how to differentiate any of those 6 things, because the only things we know how to differentiate are sine x, cos x, tan x, sec x, cosec x, cot x, e to the x, 2 to the x, ln x, and x to a power. The chain rule comes in when I change the x to something else, and it's got 2 parts to the rule. Part number 1, don't worry, just see the list on the left hand side, just do that and pretend that I didn't change it. Just ignore. So when we do that part of the rule, it's basically a case of you spot the problem. It's not a problem. You spot the function. You spot the fact that it's not an x, but you go, I'll worry about that later. So derivative of sine is cos. And see how that doesn't change? Up to this point, I ignored it. I'll come back and unignore it, but the first step of the chain rule is do not worry. Okay, derivative of cos is minus sine. Again, I'm just thinking of the function. Derivative of cos is minus sine, and then the angle in this case, or the argument, the x, just is not going to change at all. Derivative of cot is minus cosec squared. And all the way through this, I'm doing step 1 of the chain rule, which says don't you worry about the fact that it's not an x, just use the list on the left hand side. And then the chain rule says, wait, before you move on, there is step 2, and step 2 is that we must multiply by the derivative of the thing that wasn't an x. Now I know the textbook has got u's. I'm really going to recommend that we do not use u's. By the time we get to and this will only mean anything to you if you've already been taught this, by the time we get to the end of the year, no one will be using u equals, or only students that are still finding everything very, very difficult. It's a mathematically correct but notationally clunky and overly confusing way to understand the chain rule, and it's not the way that anybody uses the chain rule in reality. I've just realised that my face is on top of the x to the n down the bottom, but you do know that one from first year, so I hope that's okay. So the chain rule says, now that we've done the basic derivative, you must multiply by the derivative of the thing that was not an x. So I'm multiplying by 2 here. The derivative of 4x is 4. The derivative of a half x is a half. The derivative, oops, that's in the wrong place, haven't differentiated yet. The derivative of a half x is a half. And that's it. Let's try the ones on the top right. The derivative of e to the is e to the. But it wasn't an x. So I ignored that. And now, having ignored it, I'm going to multiply by the derivative of the thing that was not an x. Next one. The derivative of 2 to the is 2 to the multiplied by ln 2. But now, because it wasn't an x, I have to multiply by the derivative of the thing that wasn't an x, which is 4x, so the derivative is 4. And then this one. The derivative of ln is 1 over. I totally just ignored the fact that it's not an x, but now I multiply by the derivative of the thing that wasn't an x. So the thing that wasn't an x is 2x plus 1, so I'm going to multiply by 2. Now all of these you can tidy up a little bit. You could, for example, with this first one, we could move that times 2 to the front, that would be nicer. With this one, we could move the 4 to the front, and generally we would, and the minus just looks a lot nicer having numbers and then trig functions rather than bit of number, bit of trig function, bit of number. Tidying it is going to help us with the algebra that comes after we've done the differentiation. This one we would have a minus and a quarter, etc, etc. So there's sometimes a little bit of tidying up, but not a lot, and you know, in general, basically once you can do the chain rule, then after that it's fairly straightforward. So this is super duper important. We're going to do a few of these every time I see you, and I'll make them a bit harder, but it doesn't really get any harder, that's just basically it. But I'll start to sprinkle in a few where it might make you think a little bit. Okay, next thing that we need to get slowly better and better at: integration. Okay, so integration, opposite of differentiation, there's only 10 things that you differentiate, and therefore there's only 10 things that you integrate. So every single integral that you get will be one of these 10, guaranteed, because when you integrate, you are working out what got differentiated, and there are only 10 functions that you can differentiate. So the thing that you're looking at, the integral, that thing, one of those 10 got differentiated. Now, it might be disguised, it might be, we might need to do a little bit of work before we can spot which one of the 10 it is, but it is one of the 10. And there are techniques we can use. There's partial fractions, we can use algebraic division, we can use integration by substitution, we can use integration by parts, we can use trig identity. There's all sorts of stuff that we can use in order to be able to see which of the 10 it is. But at the end of the day, every single integral will come back to one of those 10. So these we're going to do, again, every time I see you, we'll do a few of these, and slowly over the year, we will make them a little bit more tricky or introduce ones that make you think a little bit. But just keep remembering to yourself, anytime you see an integral, one of the 10 things got differentiated. Same rule applies about anybody sitting at the front watching. So 3.5, and this 3, and this 2. Any numbers are just kind of a multiplier. Just think of them as somebody sitting there watching. We don't need to worry about them. They sit at the front. Okay, let's put our 3 at the front so he doesn't get lost. Okay, so we're going to look down the 10 and say, what was differentiated. The only thing that you differentiate and get cos is sine. And we know from the chain rule that we would just have ignored that 2x. So if you differentiate sine 2x, you get cos 2x. That's step 1 of the chain rule. But then we'd have to multiply by the derivative of the thing that isn't an x. In this case, the thing that isn't an x is 2x. So we have to multiply by the derivative of 2x, which is 2. But why am I talking about differentiation when we're meant to be integrating? Because differentiation and integration are the opposites of each other. And we already have 10 things that we're going to memorize. And introducing the same 10 backwards, but with the minus signs moved over, and then having to think about new ones for if it's not an x, and then having to add on the partial fractions and the binomial and the algebraic division and the substitution and the parts and all of that, and the trig, not a good way to learn it. So what I'm going to suggest to you is that from now on, you think there is no such thing as integration. Well, there is, but it's a puzzle. The puzzle is, what did I differentiate? So what we're going to do is we're going to always be thinking in terms of differentiation. And then when we nail it, the thing that you differentiate will be the thing in the integral. And then we'll know that we've got the right answer. Now, at the moment, this is not the right answer, because if you forget 3, he's just watching. If you differentiate sine 2x, you don't get cos 2x, you get cos 2x times 2. So at the moment, when I differentiate, there's this little times 2 that is popping out that I don't want. So what you do is you just kill it like that. And now, when I differentiate, I get cos 2x times 2, which cancels with my half, and now I've got the answer. And that is how you integrate. And I'll remind you, every integral you do work, so much work, and then right at the end, this is what you do, this little bit here. And it will always be these 10 because there are no more. There are no other people functions. Next one. What did I differentiate? I differentiated sec. Let's put my half there. He can just watch at the front. I'm going to leave a little gap because I might need to kill something, basically. I'll put it there. It must have been sec 2x, and that's why the derivative is sec 2x tan 2x. So now I'm purely thinking differentiation. When I differentiate sec 2x, I get sec 2x tan 2x, but then I times by the derivative, which is 2, the derivative of 2x, the derivative of the thing that wasn't an x. So I'm going to kill that 2, and I'm going to kill it like that, same way I killed the other one. It's quite violent, this process. Plus c plus c plus c. Okay, what did I differentiate? Look down the 10. The only thing that we differentiate and get e to the is e to the. So this must be something to do with e to the x squared. Because if I differentiate e to the x squared, I get e to the x squared. Chain rule. But then I would multiply by the derivative of the thing that wasn't an x. Now this is getting a little bit more tricky. What happens if we what happens if we differentiate e to the x squared? We get e to the x squared times 2x. I don't want the 2. I want the x. I don't want the 2. Kill the 2. Let's see. So that one was harder because what the chain rule produced wasn't just a number. What the chain rule produced was the derivative of x squared, which is 2x. So what we need to be able to do is we need to practice the chain rule so much that when you look at something like that, your brain can see that this is what was differentiated. That's what we're aiming for. What about this one up here? So there's a 3 that's watching, whatever. It just doesn't matter. That can just be at the front. So which of the things, if you differentiate them, which of the 10 produces a fraction? Ln. Ln is the only one. Now, modulus sign or brackets around that, it doesn't actually, from your point of view, it doesn't matter. None of the exam boards so far have taken any marks off if you don't use modulus. In fact, if you do use modulus and then you carry on using modulus, you get yourself in a right angle. Ln, you cannot do ln, the function ln, to a negative number or 0. So as soon as I write that down, that means that 1 minus 2x is positive. Otherwise, that makes no sense. In the same way that this makes no sense if x is a half. Because if x is a half, that's divided by 0, which is infinity. Makes no sense. But I haven't written at the side, oh, by the way, x doesn't equal a half. And like, for example, tan. Tan doesn't exist if the angle is pi by 2 or 90 degrees. So I didn't write at the side, by the way, x isn't 45 degrees, so that 2x isn't 90 degrees, because if it was, then tan would be infinite. I didn't write all that down, but there are these implicit assumptions and rules inside that function that we know if x is not satisfying that rule, this function doesn't even exist. You can't even do it. So technically, yes, we should put modulus signs on this ln, just in case 1 minus 2x happened to be 0 or negative. In fact, it wouldn't even solve the 0, would it? It would still be 0. But then I guess it's okay, because 1 minus 2x can't be 0, otherwise that wouldn't even have existed. Anyway, all of this, the whole point is, doesn't matter, because you can just put brackets on, it's absolutely fine. Modulus signs fine, brackets on fine, both fine. Right. Let's differentiate it. Derivative of ln is 1 over, fine, 1 over 1 minus 2x. But then I would have to multiply by the derivative of the thing that wasn't an x, which is 1 minus 2x. So the derivative here that's coming out is minus 2, because that's the derivative of 1 minus 2x, which is the thing that wasn't an x. So when I use the chain rule, a minus 2 pops out, and I do not want the minus 2. So I kill it. Now it's dead. Now it works. Now the next one is the same as the one on the top right. What thing do we differentiate and get a fraction? Well, it's not sine or cos or tan or sec or cosec or cot or e to the or 2 to the or x to the. It's ln. Ln is the thing that if we differentiate it, we get a fraction. So this, there's no number at the front, no red number. I might need to put something there like a murderer, but I don't need any numbers at the front. Ln at 1 plus sine x. Okay, differentiate. Derivative of ln is 1 over. So the derivative of ln 1 plus sine x is 1 over 1 plus sine x. But then I have to multiply by the derivative of the thing that wasn't an x, which is 1 plus sine x. The derivative of 1 plus sine x is cos x. Oh, that's what I want. Perfect. If you differentiate ln 1 plus sine x, you get cos x over 1 plus sine x. Perfect. And then last but not least, cosec squared. Okay, what is it that if I differentiate it, I get cosec squared? It's cot. And there's a 2 watching. Must have been cot a half x, because that's why it's cosec squared a half x. Now we differentiate. If you differentiate cot a half x, you get minus, because it starts with a c. All the ones that start with a c, when you differentiate them, it's negative. So the derivative of cot is minus cosec squared. I do not want the minus. And I do not want the half, because I'm going to have to multiply by the derivative of the thing that isn't an x, and the thing that isn't an x is a half x, so I'm going to have to multiply by a half x, and I don't want the half, So I don't want the minus and I don't want the half. So this is how you kill a minus, and this is how you kill a half. All of these, like before, we can tidy up the front. Like if there's a red number just watching the proceedings, and then something comes out as a murderer to kill off the thing that's coming out of the chain rule that we don't want, or coming out of the derivative that's a minus sign maybe that we don't want. All of that can go at the front, then we can tidy it up and we don't forget plus C. Okay, now integration is one of the hardest things in the A level, so if this is difficult, have a look at your chilies. It's down here. Basic integration is worth lots of marks, but it's the hardest thing to get good at. And you kind of can't get used to it and get good at it until you're really good at the chain rule, which is 2 chilies. So that's why we have to keep coming back to the chain rule, practice, practice, practice. That will really boost our integration. Okay, so let's have a look at the e to the x squared one. Let's do it 2 ways. Let's start off with differentiation. So you think down your 10, you know the derivative of e to the x is e to the x. So we know because of the chain rule that this will be that. That's chain rule step 1, ignore the problem. So the problem or the issue or the thing we noticed is that that's not an x. But the chain rule says just pretend it is and go ahead as if it was. So if it was an x, the derivative of e to the x would be e to the x. So ignoring the fact that it's not an x, the derivative of e to the x squared is e to the x squared. And then you multiply by the derivative of the thing that's not an x. So tidying that up, the derivative of e to the x squared is 2x e to the x squared. Now the integral that I set was this. So the answer is not that, because if you differentiate e to the x squared, you get 2x e to the x squared. And remember, we are trying to train ourselves to think in that direction. Don't be tempted to integrate. As soon as you start trying to integrate, it makes everything much, much more difficult. If you can contain all of your learning to differentiation and the chain rule, then that is going to make integration get unlocked for you, which is super important because so many marks. So at the moment that's not quite right, because as we saw here, if you differentiate e to the x squared, you would get 2x e to the x squared, and there's no 2 there, so at the moment it's wrong. But if I kill the 2, now what I'm differentiating is that. And this now is just someone sitting at the front, ready to kill the 2. So the integration process doesn't exist. The integration process is, have a look at this guy and think, what could we differentiate that if I differentiated it would look like that? Does that make sense? Let me read your question again. So x squared 1, it's a function within a function. Oh no, okay. I see what you mean. Hang on. So when we do chain rule, it is a function within a function, which is what the chain rule allows us to do. It allows us to differentiate not just the 10, but when I put the 10 inside the 10. So in this one I put x squared inside e. So if we use the notation that you learn in the second year, composite function notation, it would be like this. I've got e to the x and I've got another function, x squared. If I put g inside f, then the function that I get, the composite function, is e to the x squared. That's the thing that we're being asked to differentiate. Now when we do that, when we differentiate it, the thing that was just an x is no longer just an x, it's that bit. So the chain rule says, number one, first of all, just don't worry about it, the fact that it's an x squared, just do it anyway, and just, you know, yes, you are right, you've recognised that we have a composite function, and you've recognised that composite functions aren't on our list of 10, but don't worry, just do the normal stuff. And that is that step there. And then the chain rule says, stop, and now differentiate that. So can you see that if I differentiate this, I get this immediately? I don't need the chain rule again, because the derivative of x squared is literally 2x. So this one has, it's in terms of like our Russian doll structure where we put things inside other things, the outside of the Russian doll, I can't draw Russian dolls, they look terrifying. Maybe at some point I'll learn how to draw them. The outside one is the e to the. So down our list it was e to the that we are basically doing, and we're ignoring the x squared, and then inside that one is x squared inside e to the. Now I know what you're thinking, because let's say we do something like okay, shall I make it really hard? This is really hard. E to the sine cubed 4x. Now this is a really good example of why we are not using u equals and du by dx, and dy by dx is du by dx times dx by du dy by du times du by dx, and all of that stuff. If you try and do that with this one, oh my goodness, it's just such a big mess, and it doesn't need to be. So outside of the Russian doll is e to the. It's not an x, it's way more complicated than x, but it is e to the. So the derivative is e to the. That's Russian doll number one. The derivative of e to the x is e to the x. And then the chain rule says we have to stop and we have to multiply by the derivative of the next layer in the Russian dolls, which is sine 4x, and I'm going to write it differently so that we can see what's going on. It's that. So inside e to the x we have got, now this guy, and the reason I've written it with the brackets and the cubed is to make it more obvious the layer of the dolls, like which layer is on the outside, then what is it, then what is it. Because if you write it as sine cubed, then I think it confuses it. Let's look at our two functions. We've got sine 4x and we've got x cubed. Now we can put f inside g. So we put f inside the g function, which we write like this. Or we can put the g inside the f. So we're putting x cubed into sine 4x, like that. Now these are very, very different functions. One of them is something cubed and the other one is sine of something. And if we're differentiating sine of something, then the derivative of cos of that thing. Whereas if we're differentiating something cubed, then the derivative is 3 thing squared. Yeah, so the reason you always will only differentiate it once when you're using the chain rule, but it depends whether or not how many Russian dolls there are. So now whereas like if I had something really simple like e to the x squared, the derivative is e to the x squared multiplied by, and now I can just do that in my head. The derivative of x squared is 2x, done. But now I've made the Russian doll a Russian doll. So now the function that we have now is cubed. So the derivative is cubed is pull it down and reduce it to squared. Now it isn't an x. It is sine 4x. So there's another one. But we'll come to that in a minute. So the outside one was the e to the x and the derivative was e to the x. But chain rule says, but now multiply by the derivative of the thing that wasn't just an x. So we go, okay, so now we're going to multiply by the thing that wasn't just an x. So now we have to differentiate that. Okay, so now we go, okay, so derivative of something cubed, pull the 3 down, change it to a 2. But it wasn't an x. So you can't just pull the 3, well you can pull the 3 down and change it to a 2, but then you must, the rule is, multiply by the derivative of the thing that wasn't an x. Okay, we have to keep going. That bit's done, this bit's done. We probably write it like that. Okay, now the next one is sine, and the derivative of sine is cos. So the derivative of sine is cos, but it wasn't an x. It wasn't sine x, it was sine 4x. So the derivative of sine 4x is not cos 4x. The derivative of sine 4x is cos 4x multiplied by the derivative of the thing that was not an x. Now I can just do it. Now I've reached the innermost one, which is times 4. It's just 4x. And the derivative of 4x is 4. And when you get really good at this, you'll be able to do it in one line. Like that, like not gather it all together and simplify it, but you'll be able to write it all out. So the chain rule is allowing us to differentiate composite functions. It's very, very important. And depending on the algebra of the way it's structured, it can be more or less obvious what Russian doll is inside what Russian doll. And that's the thing that we need to keep practicing. Does that make sense, Priya? I guess the answer to the way you phrased the question is that I used the chain rule as many times as I had to get to the point where I didn't need to use the chain rule anymore. So I used the chain rule until the thing was one of my list of 10 so that I could just do it without having to use the chain rule. Okay, last thing for today. I've just realised, like I was looking at the time earlier and it said 9:41 in the top left. And I thought, oh, it must be 7:41. And then I thought it can't be, it must be 8:41. And now I've realised it's still 9:41. So I'm going to have to look over here, 8:30. Okay, so we've done an hour, which is a bit more than I wanted to get to this point. But let's run through these ones and then it'll be over to you. So the things that we are going to keep coming back to is the differentiation, the integration and the trig. Everything else I can teach you and then you can go off and practice. Differentiation, integration, trig, it needs regular coming back. So this is something that you won't get from the textbook and you almost certainly won't get from teachers either, this coming back thing. So that's the biggest thing I'm going to give you this year, is this repetition of these fundamental core topics, so that it becomes really, really strong in the background and you don't have to worry about them while we tick off all the other things on the spec. So, last but not least, trig. Okay, so sec, cot, cosec, look at the third letter. I think you're already quite familiar with these, but look at that third letter to see what it's the reciprocal of. So if the third letter is C, or that's not the third letter, that's the fifth letter. That's the third letter. And the third letter. Make sure that you include the theta with the sine or the cos or the tan. So never ever write this or this or this without their angle. It's like writing that with nothing inside it. It's just like an empty shell. But it's tempting, because what do teachers say all the time? Sine squared plus cos squared is 1. You listen to YouTube videos or your teacher or anything, no one says sine squared x plus cos squared x is 1. No one does, because we're lazy. We say sine squared plus cos squared is 1, and then we expect students not to write it, and if they do, we take a mark off, even though that is what we have said over and over and over and over. So make sure that the angle is always with its own trig function. If you write something like this, that means nothing. That's like writing that when what you mean is this. So the cos and the sine and the tan, they are of an angle. Sec of theta is 1 over cos of theta, not 1 over cos of theta. So that is just a peculiarity of the way that we speak maths compared to the way that we write maths and the way that we think maths, which does not help you guys at all. Okay, the first one, this doesn't require any identities. We've got lots of identities to get good at and learn, but this doesn't require any of them. So I'm just going to do this one quietly, so you can just watch. You can watch and copy, or you can not look at the screen and just try it yourself and see if you can make it work out. I do not have cos cubed. I have cos to the 4 theta times sine squared theta. I could change the sine squared theta to 1 minus cos squared theta, but that's not going to get me cos cubed theta. So option 1, I copied the question wrong from the book. Option 2, I made a mistake. Let's see if I made a mistake. I changed cot to cos over sine. That's fine. because cot is 1 over tan and tan is sine over cos. Notice how I'm not saying theta because I'm lazy. Tan is sine over cos, so if we flip that upside down, it will be cos over sine. So cot is cos over sine. Cosec, third letter S, 1 over sine. And then on the bottom, sec squared is 1 over cos squared. Cosec squared is 1 over sine squared. And then I multiplied the top and the bottom by sine squared because I didn't like those fractions in fractions. We never like fractions in fractions. So this first, I know what I did wrong. Classic. Classic. Do you know what I did? This is where I went wrong. I actually, as you know from working with me before, will always tell you whether or not the mistake I made was deliberate to make a point, or accidental and ridiculous, or accidental but actually really, really good that I made that mistake because it highlights something. And this one is the third one. This was an accident, but it highlights something really important. What I did was my brain did what all brains do when they see things like this, which is that if the two things are separated by a symbol, then we think that that symbol must be a plus or a minus, because that's the only symbol that we use, it's the only operation that we use to separate things, like physically separate them. So if I'm writing x plus y, the x and the y are, can you see that? Yes. The x and the y are separated. If I write x minus y, they're separated. But if I multiply them, I don't write this, I write this, and I squish them together. But yes, you can still see that. Squish them together. So when our brains look at an expression like this, we know that that is two things multiplied together. When we look at an expression like this, our brain says that must be a plus. And what happens is, because we're doing lots of things and we're thinking and we're using our brain, what happens is that this bit happens in the background. So our brains go, that's a plus, by the way, and then the other bit of our brain goes, sorry, what? And that bit just goes, it's a plus. You don't have to, just it's a plus. That's what my brain did. So my brain thought that I was multiplying two things added together by sine squared. So I multiplied the first one by sine squared, like expanding brackets, and I multiplied the second one by sine squared. There's the first one, times sine squared, and then times. So I knew it wasn't a plus because I wrote times, but that helpful bit of my brain is still going as fine as if we're doing the right thing here. You have to multiply both of them by sine squared. No, we do not need to multiply both of them by sine squared because it's only one thing. So I'm going to write it differently to help my little brain to see what's going on. And this is something that I recommend that you do too, is that when you have things times together, squish them together. Squish them. Because, and use brackets. If you're tempted to use a times sign, notice here, look at this. Isn't that just, oh, wait, I need to move myself or move. Isn't this nasty, this derivative? That times that times that times, look how nice it's going to be when I squish them. Much nicer. Because my brain can see now that it's one thing made up of things multiplied together. But when we pull them apart and put in the middle, that's so alien to our brains. It's so we don't think like that, we don't talk like that, we don't write like that. So our brain does its best and it says, well, if they're separated, it must be that they're added, not times. So that is what happened in my brain there. And now that I have recognised that and fixed it, then the top, I was right on the bottom though, because it was a plus. On the bottom, it was a plus. So I did have two things, and I needed to multiply both of them by sine squared in order to get what I wanted. So I'm multiplying the top by sine squared, and I'm multiplying the bottom by sine squared. That one gets times by sine squared, and that one gets times by sine squared. And now I'm going to multiply the top and the bottom by cos squared. And now everything is okay, because the bottom is 1 from the first year. And it turns out I did not copy the question wrong. I just did a silly mistake, but it highlighted a good point about time signs being dangerous. Okay, last thing and then an hour of maths is more than enough for any brain, but after we've done this question, then I will help you with whichever things you want. Didn't mean to do that, sorry. Okay. Now, Priya, are you willing to give this a go doing it my way that I taught you? Or are you still anti? Yeah? Okay. Let's flip these upside down. Okay. Solution number 1 comes from the calculator. I'm going to be in degrees. I'm in degrees. Solution number 1 from the calculator. Inverse tan there we go. Solution number 2. Now this is the only part of the process that requires any brain whatsoever, because the thing I just did is shift tan 1 over 0.6. So the first one is always just shift tan or shift sine or shift cos. So that's the first one. The second one does need a tiny bit of knowledge, which is, how do I get the second solution? Because that's different for sine and cos and tan. If it's sine, do 180 minus what you got off the calculator. If it's cos, just put a minus sign on whatever you got from the calculator. If it's tan, do 180 plus what you got on the calculator. That's the only thing you need to remember, because it's the only bit that changes depending on what the question is. Everything else is identical. So I'm going to do 180 plus that one, and I get answer number 2. And now I get answer numbers 3, 4, 5, 6, and I'm not looking here until I get to the bottom. So at the moment that is invisible to me. I'm not looking at that. In fact, I'm not looking at this either. Literally the only thing I looked at was the fact that it was tan, and then that meant that I did shift tan, and it meant I did 180 plus to get the second solution. And now I am just going to take 360 off and add 360 on. And I would do that regardless of whether it's sine or cos or tan, regardless of the domain, regardless of the angle. I'm just going to sit and get 360s added on and taken off. Always 360 or 2 pi. Okay, so far 0 brain power, which is good because it means I can use my brain for harder stuff. These guys are all 2 theta. So now I'm going to divide them all by 2, and I'm going to line them up in the same place so I know what came from what. Notice I still have not looked at that domain, and I don't care about it, because this is what I'm going to do regardless. And I know some people watching will be like, you don't need to do this because the domain says that we only want blah blah blah, but I would rather have a method that works for every question, where sometimes I do something which requires no brain and no seconds, tiny seconds and no brain. I'd rather have that and know that my method that I'm doing is definitely going to work. A lot of students don't realise that they can't do this until they get to the exam and get the answers wrong, because you learn it in the first year and you think you can do it, but if you actually try and, you can't have two decimal places, no. If you actually try to do it and see whether or not you actually get the right mark with the right angles, then if your method works, then perfect. But this is what I recommend. No graph, no quadrant, no thinking. Okay, here are the answers. Now, and only now, will I have a look at this guy. Okay, so apparently I want 400 to 700. So far I haven't got any. None. I have none so far. But that's alright, because I can just pop back up here really easily and get some more. 419.036, add 360. Divided by 2. Oh, nearly. I'll pop back up. 779.036, add 360. And it's always 360. Doesn't matter whether it's sine or cos or tan. No, always 360. Always. So the only difference between sine and cos and tan is how you get the second solution. If it's tan, you do 180 plus. Other than that, this method is the same for sine and cos and tan, which is why there's no thinking required, which is why it's so lovely, and it gets you the right answers. So we're going to add on 360. Always 360. Divide it by 2. Yay! I'm just going to go back up and check another one. So I'm going to do 1139.036, add 360, just in case. And then divide it by 2. No, that comes out too big. 749, it comes out too big. So I've picked up one solution so far. And then the other one, those three are no good. I need to go back up to 599.036 and add on 360. And I'll add on 360 again. And I'll add on 360 again, because that's how many times I needed to do it last time. So there we go. And then divide by 2, divide by 2, divide by 2. Yep, we want that one. 1319. Yep, we want this one. I don't think we're going to want the next one, but like, how long does it take me to go check? 1 second. 17679 divided by 2. Yeah, that's too big. 839. Too big. So there are 3 answers. Now, if you can use the graph method or the quadrant method and do that question and get those answers reliably, brilliant. Continue. The vast majority of students can't. So this method is one that you can just take and use. We'll practice it regularly, either with sine or cos or tan, so you get used to that second solution. But then the method is just to do with 360 or 2 pi's, taking off 360, adding on 360. Okay, we're going to move on to, Priya, you asked about moments and about drawing, specifically drawing the force diagrams, is that right? Of the specific situation where you have a beam like this. What else could we have? We could have We could have a seesaw-y, beamy type thing like that. We could have something hanging from some string. Can I think of anything else that would be parallel force? You want just parallel forces? I guess. Oh, we could have something like that one that you sent me earlier today. That thing where it's like a book about to fall off a shelf. Oh, non-parallel. So these ones are all parallel forces. Not that it makes any difference, okay? The steps for moments are going to be identical. 1, we're going to draw the forces on. And then 2, we're going to resolve all forces into up, down, left, right. So if you have non-parallel force, if you have non-up, down, left, right forces, then you have to do step 2. But if you've just got parallel forces like these, then you don't have to do step 2. 3, up is down. 4, left is right. 5, moments equation. 6, simultaneous equations. That will work for every moments question. But I think the thing that you're asking about here is specifically how do you draw the forces on? But I'm not sure if you mean ones like this or ones like ladders and stuff like that. So let me know. If it's this one, then let's go through our 5 forces. 1, 2, 3, 4, 5. Weight. And then these 2 are only for when we've got 2 things in contact, like a particle on a slope or on the floor, or a beam leaning against something like a ladder. So these are like your contact forces, which is normal reaction and friction. But in these cases, we are going to have it there and there. We are. I'm lying. Yeah, okay. So these ones, we've got weight, then we've got normal reaction or friction, no frictions in these ones. We've got tension in the string, different tensions, unless they tell us it's the same. We've got the weight, which is either coming from the centre if they use the word uniform, or coming from not the centre if it's non-uniform. That's it, because then there's like an engine or a push or like a hinge or something like that. We haven't got that in any of these situations. So that's it. That's the force diagrams for these ones. Now, if we now make the diagram a little bit more complicated, and I just need to specify not AQA. AQA can have hinges, but not ladders, and not things like this, which OCR and Edexcel put in, things like that, and a ladder. And the thing that makes this not AQA is the friction, not because it's a different spec, but just AQA said that they don't want to assess friction, like F equals mu r, they don't want to assess that in the same question as moments. That's what the chief examiner told me. So I will keep checking that, because technically, oh yeah, so no, there you go then. But okay, so let's do a hinge then, because you could get a hinge. That's string. So it's got a hinge there, and then it's got a piece of string like pulling it up. So you can still have non-parallel forces, you just won't have any friction. And the 2 that I drew on the left, there would be friction here and here and here, unless the wall is smooth, there would be friction. And here, unless the ball thing is smooth that it's leaning on, or the peg or whatever. So it makes no difference to the steps, It just means that in AQA you won't get those specific scenarios because they require friction, and you're not going to have friction. But you will still get ones where you have to do step 2, so like this one. So let's put our forces on. We have the weight. Now the reaction here, there's no friction, but there's a reaction at the hinge, and we don't know which way that's going. It's going like let's think, that's going that way, so it's going that way and that way, or maybe it's going that way and that way. We don't know. So what you do when you don't know the direction, and this is true with friction as well, if there's no way of knowing whether friction is going to go left or right, or up the slope or down the slope, you just put it going whichever way, and then if it comes out negative, it went the other way. And that's not going wrong, that's how you work out which way it's going. So the reaction at the hinge, we're going to split it up into X and Y, and it really doesn't make any difference whether you put Y up or down, or put it up. If it comes out negative, it means it went the other way. So that is weight, tick, reaction, tick, no friction, tension in the string, which you draw like as if you're drawing the string. And then that's it, there's no engine. We've done the hinge. So step 1, force diagram. Step 2, doesn't matter what situation it is, resolve into up, down, left, right. So that T, do not want it like that. We want how much up and how much left. So we need to know what the angle is. Probably we know that angle, in which case this is T cos and this is T sine. But if we knew the other angle, if we knew this angle, then this would be T cos and this would be T sine. So whichever one is adjacent, cos is adjacent over hypotenuse, whichever one is adjacent to the angle, next to the angle, touching the angle, that one is the cos and the other one is the sine. So the T, we will break that up into U, and this, say that's the angle that we know, and that's theta. This is T sine and this is T cos. Okay, and then you do up is down, ups are Y and T sine theta equals down, which is mg. Left is right, X equals T cos theta. We'd do moments probably at the hinge, and then we would have simultaneous equations. Was there any other scenarios that you've seen that I could help by drawing the force diagram for you? But obviously not ignore ladders. I'll try and get my lighting a bit better for tomorrow as well. Not that it particularly matters, because the main thing is the screen, obviously. I'm quite impressed I got it to work, to be honest. And thank you for coming and supporting me on here. We'll see how it goes. Alright, is there anything else that anybody would like me to go over today? If not, I'll see you tomorrow. Yeah, so I'm trying to remember what, so when I did non-parallel forces, did I do like a, was it like, because I won't have done a ladder because of AQA students not needing a ladder, was it something like that? Maybe? Where that's theta and that's alpha? I can't imagine another, I'll have a look tonight at all the moments questions, but I can't imagine anything else that's got forces that we need to resolve and also isn't a friction one. I mean, this you could have this situation, couldn't you? You could have, this is the ceiling and there's two strings, but they're not hanging straight down, they're like at an angle, you could have that. In which case, weight, number 1. Number 2, reactions, friction, no. Then 4th is tension, yes. So we would be resolving both of these. Let's call that T1 and that T2. No engine, no push, no hinge, so that's the end. And then to resolve them, up, left, up, right. Whichever one is adjacent, that one's cos. So this one's T2 cos. And this one's cos, depending on which angle you know from the problem. And then up is down, left is right, 1 moment's equation that we might not even need. Well, we probably would need it for part B or part C. Simultaneous equations. Yeah, so Donia, what I am doing is in the evenings I'll do YouTube, and my plan is to get through, I don't want to call it get through. My plan is to cover all the content, definitely for the second year. There is a possibility that this year I'll just do second years and then next year I'll introduce first years, but I'll have a think about it. But definitely for second years, I want to cover all the content starting now, so I won't assume any of the stuff that we already did. But my focus is going to be on this central spine, and then we will weekly introduce bits and bobs from the other bits and bobs. And we can pretty much do that in any order, to be honest. So I can do it in the order of the textbook if you want, or I can do it in the order of like what you're just in the mood for that day. But we need to keep that central spine really, really strong by coming back to it and back to it and back to it. So all that's going to be free. That's just going to be on YouTube. I'll do that all the time. And then on YouTube, there is a link in the description, and then you can use that to book one-to-ones. So what I'm hoping is that I will get enough one-to-ones in the day, or like, you know, up to whenever I do, up to the evening, to pay the bills. That's the plan. If I can just get enough in the day to pay the bills, then we're all happy, because then I will still have my time to do it in the evening with you guys. And I hope build up a little group of people that are doing the exams in 2024, and you know, we'll all work together and we'll get the content covered, and then we'll look at predictions of what last year. I'm so proud of myself. Last year my AQA predictions for paper 1 were like perfect. Like, if you'd done my prediction papers for AQA, and the other two as well, they were good, but AQA was like freakily good. Like, if someone had seen my prediction papers, they would think that I'd had access to the paper. I was very pleased with that, because I put a lot of time into those predictions, and I used some sneaky little rules to work out exactly what they were going to put in, because they have to stick to rules, you see. They can't just chuck a load of questions in. There's rules about the number of marks for different topics, and also how that averages out over a 3-year period or a 5-year period or a 7-year period. So by looking at those averages as well, we can work out what they're a bit low on, so that we know what they've got to top up. So yeah, so in theory, Priya, in theory this will have been recorded. I don't know if it will or not, because it's the first time I've ever tried to do YouTube, but in theory this will have been recorded, so it'll go up. But what I might try to do is edit it a bit and chop it up so that it's like smaller bite-sizey bits. Yes, you'll be fine on it. Honestly, you will be totally fine. It's not like, it is a hard subject and you can't cram it. That's what makes it difficult, is that unlike you, there are going to be so many people in May saying, I'm alright on like this, but I can't do differentiation or integration or trig. And it's like, obviously there's things we can do in May to make it a bit better, and we can work on the other things as well, and we can be strategic and but boost the grade. But maths takes practice and it takes time, because you have to have gaps between the practices to build the links that you need to be able to problem solve the way you have to problem solve. So it takes time, but if you have time, which we do, then it's really not rocket science. Like, almost everyone can get an AA star provided we have enough time. Honestly, almost everyone can get an AA star provided we have enough time and we use the time the right way. But it's fine, because we do have enough time and you are using it the right way, so you will be totally fine, I promise. Okay, should we leave it for today then? And I will work out whether or not I recorded this and what is going on that screen, and see you tomorrow. And I'm just going to focus on second years for now until I get comfortable with all of this stuff, because that is obviously the most important, because it's, you know, you've got the least time. First years we have got a longer time. Lovely. All right guys, see you tomorrow at 7:30. Right now you're going to watch me spend ages here trying to make it stop. Oh, stop streaming. It will not